Welcome to the study of the Kolbe-Schmitt reaction. This powerful chemical process allows us to transform simple phenol into salicylic acid, which serves as the fundamental building block for producing aspirin and other important pharmaceuticals. Why do we study this specifically? It is one of the most cost-effective ways to introduce a carboxyl group onto an aromatic ring. Understanding this mechanism is key to mastering industrial organic chemistry and large-scale synthesis. The journey begins with phenol and a strong base, typically sodium hydroxide. The base deprotonates the phenol to create a more reactive species. This initial step is crucial for activating the aromatic ring for the subsequent steps. By removing the acidic proton from phenol, we generate the sodium phenoxide salt. The negative charge on the oxygen increases the electron density of the benzene ring through resonance, making it highly susceptible to electrophilic attack. Our next player is carbon dioxide. While CO2 is a relatively weak electrophile, the highly activated phenoxide ring is powerful enough to react with it. This interaction is the heart of the carboxylation process. To force this reaction to occur efficiently, we apply significant heat and high pressure. These conditions help overcome the energy barrier and ensure that the CO2 gas remains in close contact with the phenoxide salt. The phenoxide ion attacks the carbon dioxide molecule. Interestingly, the attack occurs primarily at the ortho position. This is due to the stabilizing coordination between the sodium cation and the oxygen atoms of both the phenoxide and CO2. As the bond forms, the ring temporarily loses its aromaticity, creating a high-energy intermediate. This state is unstable, and the molecule will quickly seek to regain the stability provided by the aromatic pi-electron system. Aromaticity is restored through a proton shift. The hydrogen at the ortho position is removed, allowing the electrons to return to the ring system. This step is energetically favorable and stabilizes the resulting complex. We now have sodium salicylate. At this stage, the product exists as a salt because the environment is still basic. To obtain the final acid, we must proceed to the final chemical workup step. By adding a strong acid like sulfuric acid, we protonate the carboxylate and phenoxide groups. This acidic workup converts the salt into salicylic acid, which then precipitates out of the solution for collection. Let's look at the stoichiometry. Under ideal industrial conditions, 1 mole of phenol reacts with 1 mole of carbon dioxide to produce 1 mole of salicylic acid. High yields are achievable through careful control of pressure and temperature. Why ortho and not para? The sodium ion acts as a bridge, or a chelate, holding the CO2 molecule close to the ortho position. This proximity effect ensures that the reaction is highly regioselective for the ortho product. Looking at the energy profile, we see the initial activation energy required to form the intermediate. The subsequent rearomatization step releases a significant amount of energy, making the overall reaction exothermic and thermodynamically driven. In industry, the salicylic acid produced here is treated with acetic anhydride to create acetylsalicylic acid, commonly known as aspirin. This sequence is one of the most successful applications of organic synthesis in history. To summarize, remember that phenol must first be converted to phenoxide. Carbon dioxide then attacks the ortho position under high pressure, followed by acidification to yield the final carboxylic acid product. Quick check, which factor ensures the CO2 attacks the ortho position? The correct answer is the coordination of the sodium cation. This chelation effect is what makes the Kolbe-Schmitt reaction so unique and predictable. Generated by Vision Solve AI.